Okay, with the control scheme that I just introduced, let's examine if human posture control could be described in terms of optimal control perspective. Okay, so the very first step is starting with the equations of motion. Equations of motion of the human posture. Let's adapt two-segment model. So there are four state variable, theta 1, theta 2, and theta 1 dot, theta 2 dot. And using this state variable, we make the equations of motion into a state variable form because we want to formulate the optimal control model. So for the objective function, there are quadratic of the error, the deviation for the angle from the upright, and the control cost. Okay, so the next step is how we can determine Q and R. Since we have a four-state variable, Q is 4x4 matrix and R is 2x2 matrix. And then this one is a relative magnitude between the Q and R. Okay, and then the first one is a penalty for the ankle torque, and the second one is for the hip torque. Okay, so if you have a specific, muscle, if your body prefer not to use hip muscle compared to the ankle muscle, maybe those term might vary. Okay, but in general, same muscle work will be reduced to minimize the metabolic cost. So I'm going to assume that those relative costs, relative penalty for the control cost for the ankle and the hips are considered to be equal. So that R is simply identity matrix. Okay, so that make the R matrix simple. So let's move on for the Q. First, four variables are penalty for the angle deviation, and the last two by two values penalize for the velocity deviation. Okay, so as far as we have a smaller angle, that'll be more like a prioritized assume. That's what we assume. So maybe angle deviation minimization will be preferred more than the velocity. So make the other term to be simple, like all zero except the Q angle penalty. Okay. So original 4x4 Q matrix and 2x2 R matrix now become simple as identity for the R, and Q is only having 2x2 matrix. Okay, so that is a scale factor here because we set R as identity matrix. Okay, so we could, it's only 2x2, so we can just try many combinations for the Q matrix, arbitrary manner by trial and error. However, Q is kind of a philosophy that what do you want to minimize? Not just, that's going to be multiplied by the factor for the theta 1 and theta 2. So what is the meaning for the Q if you set it as, say, like 1, 2, 3, 4 or something? So are there any physical variable that could match with the Q11 vector? One possible suggestion will be we'd like to maybe minimize the center of mass variation or the upright deviation from the earth vertical, or we'd like to minimize head position deviation because all the sensors like a vision and vestibular for the motion sensors are located in the head. So those are some possible candidate for minimizing factor. Okay, so let's work on this. So if you want to minimize a center of mass, where is the center of mass here? You have a center of mass for the upper body, you have a center of mass for the lower body. So if you have some algebraic combination for that, you can calculate the center of mass. So if I set it up, this one as mass normalized center of mass location for the first segment, and this one is for the second segment. Okay, so I have certain like a parameter, like a vector multiplied by the x to demonstrate the x of COM. Okay, so that's what we call the C of COM transpose. If I minimize a center of mass quadratic form, that is going to be formulated in terms of C and x, and that's going to be formulated as x transpose something in x, which is Q11 formulation. So by minimizing the center of mass variation, we could identify the Q11. Okay. In the similar manner, if I want to minimize the upright posture is just simple summation for theta 1 and theta 2. So 1 value so that you can calculate C up. Or in a similar manner, you can minimize head position. Head position is multiplied by the theta and the leg length, okay, body segment length. and then you can multiply by them to figure that out, the head position. So to summarize, there are three different objectives, like minimize the center of variation, will give the Q11 in terms of COM in its transpose, and for the upright and the head position minimization also gave us the idea what Q11 form could be formulated. Okay. Okay, for each different Q11, I might be able to find the optimal K, and I'm going to respond how those optimal K will generate the simulated postural response. Okay, one way to examine the postural response is looking at the theta value over time, but this is a two-segment, like a body, correlated body. So in terms of time trajectory, we can also look at the joint coordination point of view. So for example, if you draw the x-axis, if you set the x-axis as the ankle angle and y-axis as the hip angle, the trajectory for the theta angle and the hip angle can give us how you could coordinate your upper limb and lower limb. So for example, if you have, and then for positive, like a first quadrant means positive lower limb angle and positive upper limb angle. So you are about to fall, right? You are leaning a lot forward. So second quadrant means you have a negative lower limb, means like you push your hip backward, and while you are leaning upper limb forward, right? So that's the configuration for the body for each quadrant. So suppose you have this posture, what you want to do is just going to the origin. You want to standing upright. So maybe you can just, reduce your lower limb back and upper limb back. Okay? That's one way. Or if you want to minimize the center of mass deviation means if your lower limb move backward, you want to move your forelimb forward in an opposite manner, right? Compensatory manner to maintain center of mass stays there. So in that case, this trajectory will demonstrate the minimization of the center of mass deviation. Okay, so that's what we are going to look at, the joint coordinate perspective of those solutions obtained from three different objectives in the next slide. Okay, so for ankle angle as an x-axis and y angle as a hip angle, minimizing center of mass showing this kind of trajectory. Okay, suppose you started with forward-leaning posture. Instead of directly coming to the origin, your control make the motion, the postural behavior as moving the lower limb back while your upper limb moving forward, means compensatory behavior. And then at certain point, you just reduce all of your body posture to the origin. That's how center of mass minimization optimal control generate. Okay. How about the upright? If you minimize the upright, if you are in this posture, your action is just different from the center of mass minimization. Your upright division minimization directly moves you toward the origin. Okay. But your upper limb moves first. Upper limb recovery goes first. Okay, goes first, and then your total body moves toward the center. Pretty different behavior from center of mass minimization and upright minimization. Okay, for your head move displacement minimization shows that you have this forward leaning posture. Your first your upper limb is moved backward, okay, while your lower limb also moved forward, okay, like this. Okay, so your head movement focus on the upper limb movement with the overshoot even, and then at certain point you're converging toward the origin, the upright posture. Okay, so by having three different optimization penalty weight, the Q11 matrix, you will have a different optimal K, which will give us a different postural response. Which one do you think will be most likely with the human behavior? Answer is on the next slide. Okay, so instead of just only exclusively having either the center of mass or the upright, why don't we just combine both? Okay, so, why don't our Q matrix would combine both penalty, like penalizing center of mass deviation and the upright. So if you have a weight vector, you have a reciprocal weight vector, and then since you want to minimize the effect with the W value itself, the magnitude itself, you can normalize them. So this is the proposal for the penalty Q factor for the LQR. So you have a total like a scaling factor compared to the R vector, R matrix, sorry. And then you have a relative weight for the center of mass suppression compared to the upright. And then for the numerator, we have normalization with the singular value. Okay. So what it looked like is here the solid line is a simulation and dashed line, dotted lines are data. Pretty well representing data simulation by simulation of optimal control. So those results were obtained by the optimize the control parameter as mu equals to 0.997 means mostly the center of mass deviation matter. Okay, you want to minimize the center of mass deviation and sigma 1.4. So like combination for those regulation criteria, the center of mass were behavior were well represented by the optimal control. And with that, okay, we were able to describe the behavior using the optimal control. What that means is it seems like your central nervous system, your brain seems to be care not only the center of mass deviation, but also the economy of movement, your control cost, your muscle metabolic cost. That's the interpretation of the result. So our hypothesis saying that our control K could be identifiable using the optimal control scheme. Yes, the hypothesis has been proved. And this is another example how we can use our control knowledge or control discipline to understand human posture control.